Okay, so yeah, welcome everyone to this lecture then, under these new circumstances. And yeah, what I want to do today. So, of course, if you have questions about last week's lecture, then we can discuss them later. Maybe it's a bit easier to do that during the exercise session after this lecture. And what we want to do today is to prove bulk universality under for Wigner matrices if they have satisfy a moment matching condition on the entries. So let me maybe start by recalling the basic definitions and also the statement. So what I defined last time is what it means that two Wigner matrices H and H prime match to order n. So H and H prime are Wigner matrices, as we have already used in the last semester where we introduced them. And then we say that H and H prime match to order n if for all I and j, so for all entries, and all k and l which run from 0 up to n, such that the sum of k and l is smaller than n. We have the following condition on the moments. Sorry, this one. So we have that if I take the expectation of a mixed moment hij to the k, hij bar to the l, and I compute this moment of h, then I get the same as if I compute the same mixed moment, so hij prime to the k, hij prime bar to the l. And yeah, we assume that all of these moments match as long as the sum of k and l is smaller than n, and yeah, k and l can run through all integers, positive integers from 0 up to n under this condition. Okay, and then the basic object that we want to analyze is the local k-point correlation function around an energy E, which lies between -2 and 2. And yeah, just to draw it once more, of course, this -2, 2 means that we're in the bulk of the semicircle. And then yeah, the object we want to analyze is this local k-point correlation function around E, which looks as follows. We take the k-point intensity measure, or yeah, sorry, not correlation function, but k-point intensity measure, and then we shift and rescale it. So everything is now centered around E, and rescaled to go down to the scaling of the typical eigenvalue distances. And you can also think of this as the k-point intensity measure of this rescaled process, where we center all eigenvalues lambda e, which are the eigenvalues of h. We center them around an energy E. So we subtract E. I hope this is. If you cannot read something, then of course you should complain. And then we center them around E, and then we rescale everything in such a way that yeah, sorry, there's another typo. This should of course be a delta. So we shift all eigenvalues such that they are centered around E, and then we rescale them such that around E we are on the scale of the typical eigenvalue fluctuations, and then we sum up these Dirac measures. So then we get some stochastic process. And then the main theorem, so the first main theorem of this lecture, which we wanted to prove, is theorem 2.2, which proves bulk universality, because yeah, as I said before, the fact that the E lies between -2 and 2 means that we're in the bulk. And it reads as follows. So as in the definition before, we have a matrix. We have two Wigner matrices H and H prime. They are Wigner matrices, and we assume that they match to order 4. So I somewhat already motivated last week why this order 4 comes up, and but this we'll also see in the proof, which we'll go through next. And then we have the following statement. So we find, so there is a Xi positive such that for any fixed k, E and the function f, we have the following. If I test the empirical the local k-point intensity measure around E for my function. If I test this with respect to this function f, then I get this, and I compare this to the same result when I replace h here by h prime. So I compared with the local k-point intensity measure around E for h prime tested against f. Then this has a small error, n to the minus. It's also readable, n to the minus xi. Okay, and yeah, and then last week I gave you some ideas how to prove this. So the basic principle was that we wanted to follow the Lindbergh proof of the central limit theorem. So we wanted to write these two. We wanted to write these two quantities in such a way that we can write it as a telescopic sum by comparing it. And in this telescopic sum, we want to successively replace one entry of h by one entry of h prime, and then step by step control this error, and then sum up all of these error terms. And that was the basic philosophy. So we want to replace one by one the entries of h by entries of h prime, and then replace the represent this difference here in terms of the sum, in terms of a telescopic sum, and then control by this moment matching condition control each summand of this sum and make it very small by assuming that to match to a sufficiently high order. Okay, so now I'll go into the proof, and I guess you all know this feature that you can always, if you go to this bar and then you can press annotate, and there you have the option to save, so you can save the current shared screen, and I'll try to always fill up one screen, and then I'll tell you that you should save it now, and then I'll go to the next screen, so you don't have to take notes all the time. Okay, and okay, so now we want to go into the proof, and what we already discussed last time is that in some sense we have to control derivatives. So we want to compare. So the basic philosophy last time was that so that's already what we saw last time, is that we want to compare. We want to write everything in such a way that we have an expectation of. We have a function f, which is not the little f we had before, but we will see how to choose it. And we want to write this in such a way that this is somehow the expectation of f of h gamma minus f of h gamma minus 1. And then we sum up from all gammas. And then we want to prove that this thing here is small. And what we saw last time is that one can use some kind of Taylor expansion here, and one can use Taylor expansion here, and then one gets in naturally the moments of entries of h. And but then the problem was that one has to control the derivatives of this function f, which we don't know how to choose it yet. And here the idea was that one can bring in the resolvent, because the resolvent we can control very well by the local law, and moreover the resolvent also its derivatives. So essentially the derivatives are again entries of the resolvent square, or like products of order 2 of entries of the resolvent. So these we can control again by the local law. So the first thing is that the first step that we have to do is, that will now be the first computation, the first part of the proof. We want to express the correlation the local intensity measures, so the rho and h e k, the notation is a bit complicated in terms of the resolvent G. Well, maybe I just recall it. Okay, and this we will do by smearing out this measure. So we want to smear out this measure here by an approximate delta function. So then we get some nice measure which has a density, and this we can work with much better. So this is what I want to do next. So this is done via smearing out of the approximate delta function, and this function we'll choose well, naturally, because all this business of resolvent and Stieltjes transform, this following function appears. So we have the imaginary part of 1 over x minus eta. So eta is again the spectral scale, and then of course this imaginary part is easy to compute. It looks as follows, and then maybe one important observation is the following, that yeah, how this relates again to the resolvent. That's maybe something which we've already seen maybe last semester. Just to recall it, if I have a sum j from 1 up to n, theta eta of lambda j minus x, then you can just plug in all of these, use the definitions, and then you end up with the following, and you realize that those are the eigenvalues of the resolvent at x plus I eta, and then this is the imaginary part of the trace. So yeah, so it looks as follows. It's the imaginary part of trace x plus I eta. So just to see how this relates to the trace, how this relates to the resolvent, because this, sorry, now I was too fast. So how this relates to the resolvent, and now so yeah, maybe now if you want, you can use this function with the picture. I hope to save it. I hope you all found it, and so maybe you give me a sign once you're done, or if you have problems, you can also tell, send me a message or raise your hand or something. And then okay, maybe I can continue. So what we then want to do next is that now we have to choose an eta, and the eta we will actually choose a little bit smaller than the typical eigenvalue spacing, and that will then allow us to kind of understand how really the eigenvalues behave very close to E, very close to E, and then on the typical eigenvalue spacing. So for that we fix an epsilon, and we choose an eta which is, as I said, a bit smaller than the typical eigenvalue spacing. So it's n to the minus 1 minus epsilon. So yeah, now this minus here is important. So yeah, maybe I should remark this. So slightly smaller. The typical eigenvalue spacing. So a priori, of course, our local law is not very strong there, but this moment matching technique will help us to improve this, as we will see a bit later. And now we can write everything in terms of the microscopic scale. Macroscopic scale. So on the microscopic scale, we have then the eta tilde, which will be n times rho e times eta, and that's rho e into the minus epsilon. Okay, and now we will smear out this f with the following construction. So so what we will do is we will define an f eta tilde of u1 up to uk, which is defined as follows. It's a convolution with these theta eta. So we integrate with respect to v1 up to vk. This integral runs over rk. So we take the original function, evaluate it at vk, and then yeah, we take the convolution with these theta eta tilde. So u1 v1 up to theta eta tilde uk minus vk. Okay, so yeah, this I will call equation dot, because we'll come back to this. And maybe just as an idea, so in some sense this theta eta always averages over a small interval. So maybe as a sketch, maybe for k equal to 1. So you might start with some function f, which oscillates quite rapidly. Yeah, something like this. This is maybe the function f. And then with this construction, I get the following function where these bumps here, they're somewhat smeared out. Okay, so the picture will look like this. Maybe you've seen it. It's somewhat convolution with a smooth function. So yeah, you will still have some kind of bumps, but they are much smaller because they're averaged out. And I guess the number is probably, let's restart. The number of bumps is probably similar, or at least not bigger. And then this is somewhat the idea that this mirroring out gives you, just as a side remark. Okay, and now we will have a new goal. Namely, we want to prove now first the statement of theorem 2.2 where the f is replaced by f tilde. So show theorem 2.2 with f replaced by f eta tilde. Okay, and then we will have a theorem or a lemma which tells us that that we can go back, and once we know theorem 2.2 for f eta tilde, then we can go back to the original one. So then go back to f using lemma 2.5, which we'll see below, and that's a consequence, which will essentially be a consequence of the local law. Okay, so yeah, maybe now is another good time to take a picture of these nodes. And now the idea is that if I start from this function f eta tilde, then it's easy to bring in the So if I test this function f eta tilde as we have to do in theorem 2.2, if I test here, if I have here f eta tilde, so maybe so here if I had here an f eta tilde, Then I have to test this against the local k-point intensity measure. And then by the definition of f eta tilde, it will be easy to bring in the resolvent. And then we can reformulate the whole, we can reformulate this statement in terms of the resolvent, at least if the f's are replaced by the f eta tilde. And then we can use the machinery of the resolvent, and in particular we can make this idea here work for the resolvent by using the local law and these moment matching assumptions. Okay, so what I have to do now is I have to understand the following integrals. So I have to understand f of eta tilde u1 uk, and then the local k-point intensity measure. I'll now focus on h, but of course you can do the same computations for h tilde. Okay, and now by plugging in the definition of f eta tilde, the definition up here in dot, and using Fubini, we can rewrite this this integration in a more slightly different way. So it looks as follows: I get an f of u1 up to uk, then I change the order of integration, and then I get a new function p e h e and eta tilde. The notation is a bit complicated, and but yeah, this is just notational complication. I guess the interpretation is quite clear. So so this you should think of as being a smoothed out k-point correlation function. You know that well, we saw it somewhat on the exercises, that if your matrix H has absolutely continuous entries, then this also will have a density, but in general it's just a measure on RK. But if you smooth it out, so with this function here, which has this delta, it's approximating delta function in there, then you actually get you can transport the smoothing from the function f to the measure here, and then you get a k-point correlation function. Also in the general case, and well, I still owe you the definition of the row, so of the p, where p n h e eta tilde k is defined as follows. It's just, yeah, as I said, you just move the definition over by using Fubini. So it's theta eta tilde u1 minus v1, and then theta eta tilde uk vk, and then we have the local k-point intensity measure. So dv1 vk. So yeah, maybe I should have chosen other names, but well, let's leave it like this. And yeah, the way you should think of it is this is a smeared out well, yeah, local k-point intensity measure, or oh yeah, maybe better correlation function. So, but just to remind you that in general, the k-point correlation function will not exist for an arbitrary measure, for an arbitrary h, but only if the entries are absolutely continuous. Okay, and now what we want to do, we want to rewrite everything back in macroscopic variables, and then it will be obvious how the resolvent comes in. Okay, so so yeah, we have with macroscopic variables, we have the following. So now I call them xi. So this is centered around E. Then I have ui, and then the spacing So with these variables, we have the following. If I look at, maybe I should, this here should be a VI. So I have a P HE, now it's, it's the same thing as before. We still evaluate it at the places, at the U's. And then, no, sorry, I confused myself. So this is a U. So the xi is just a function of ui, and these things here anyway is fixed. And now we want to express this here as a function of x. Yeah, we also rescale the measure. So this needs a little computation. Let me give you the result first, and then I say something about the proof. So there's a scaling factor. Then I have a theta now of eta. Then xi, x1, y1, and so on, xk, yk. And now the measure became the normal, the standard k-point intensity measure. So now we moved all of the rescaling and centering at E. We moved this into the thetas, and yeah, as I said, this needs a small computation. And the main thing you have to notice there is that the theta of eta tilde of u, so this following expression, which is in terms of the microscopic variables, if I can express this in terms of the macroscopic variables as follows. This looks like this, and then I have a theta of eta E minus y plus u over n. This is just a simple computation, so maybe now is another good time for a picture. And yeah, this is, yeah, to come from here to there is just a simple computation, and in this part, this relation down here is the very is the important step. And now here we have the k-point intensity measure without any rescaling, so we can easily express this in terms of we can use the definition of rho n h k, and then it will be obvious how the resolvent comes in. So by definition of this rho n h k, we get the following. So yeah, so I want to express this here now directly in terms of the eigenvalues. And to that end, I recall that this here, so if I test the k-point intensity measure against the function, then that's the same as taking the expectation of these sums of distinct indices over this function we are looking at. So this is the same as, well, scaling factor stays the same, and then I get an expectation. Now I get this sum over distinct indices, and then I have to evaluate the function at eigenvalues, or in place of eigenvalues. So theta eta xk minus lambda I1, well, in this form. So x1 minus lambda I1, and then xk minus lambda ik. And yeah, so this is the general formula. We just plugged in the definition of the k-point intensity measure, and now, as I indicated to you before, these things here, they will yeah, they can be expressed in terms of imaginary parts of resolvents and their traces. So that will look as follows. And now I will restrict to the case k equal to 2, because the general case, already in the case k equal to 2, so this k will be 2, I have all complications, and the rest just needs more, well, a bit more complicated notation, but there are no additional complications coming in. So from now on, we restrict to k equal to 2. And then, yeah, maybe I should remark k equal to 3 is similar with a more complicated notation. Okay, so now I explicitly want to write out what this function looks like when k is 2. So I just have two variables, u1 and u2. And then it looks as follows. So in principle, here I have the sum over I1 and I2 of distinct indices. And I will write it in the following, that I first allow a sum where I allow for all indices, and then I'll subtract those contributions where the indices are the same. So the factor here stays the same, n rho of e squared. Then, as I said, well, there's the expectation here. Then I have both indices now without constraints, theta of x1 minus lambda I times theta eta x2. Now recall that the x1 and x2 are a function of u1 and u2, minus lambda j. And then I have the expectation of the term where I is equal to j, theta eta x lambda I x2 lambda I. Okay, and now I want to rewrite this in terms of, well, in terms of first I want to replace the lambdas by ages, and then putting the trace at the appropriate place by functional calculus, and then we will see that we can actually write it as a resolvent, or as a combination of resolvents. So there's this same factor, and then I get an expectation. So now this first factor only depends on I, and the second factor only depends on j, so I can put the j sum I can put here. So what it will end up with is that this is theta, a trace of theta x1 minus h times the trace of theta eta x2 minus h. And here both of them are the same. So this is well, in the matrix sense, this is the h evaluated at the product of this function, and then I take the sum. So this looks as follows. This is the expectation of the trace of theta eta x1 minus h, theta eta x2 minus h. Okay, and now we can identify that this here is actually these thetas. They're always 1 over pi times the imaginary part of the of the resolvent. So it looks as follows, that there is now we get an additional factor pi and eta squared expectation of the trace imaginary part of G at well, I want to write Z1 trace imaginary part, and maybe I should already remark Zj is xj plus I eta, G Z2 minus expectation of trace imaginary part G Z1, imaginary part G Z2, were evaluated at this. I evaluate at the ZJ here, and I used the following, that theta eta xj minus h is the same as the there's a 1 over pi imaginary part G of ZG, and okay, maybe you can save this part here again, and then I just will show you this well, I will motivate, we'll go back to the definition of theta so that you can see how this here arises. So it's really, if we go back to the definition, it was here. So now if the x is if the x is x minus h, then you get an x minus h here. So this is a resolvent, and then you have here the imaginary part. So yeah, this is the basic definition, and which gives you the identity that we want. Okay, and now we will actually have two lemmas, and then these will together prove. These will together then imply the theorem 2.2, and then the rest of the work is to prove these two lemmas. And maybe here I should remark one more thing. So this here is of course the same as Gj minus, and then you this here is the same as Gj, and here you would have a star, but this is nothing else than, if I star the resolvent, then I just complex conjugate the spectral parameter. So what we really have to understand is only entries of resolvents at well, now all spectral parameters which are not on the real line. Okay, and then yeah, maybe I should already remark this. So this completes the proof of theorem 2.2 up to the next two lemmas. Next two lemmas. Okay, and I will state at least one of them, and then we can make a short break. So we start with lemma 2.4, which is really the core of the proof, and this goes under the name of green function comparison. So there the idea is that if I have two Wigner matrices which match to a sufficiently high order, then the green function will be close, or expectations of green functions will be close. So how is this formulated? Well, we start with, as before, let H and H prime be two Wigner matrices that match to order 4. We fix an E and an epsilon. Epsilon should be between 0 and 1 over 20. And then we find xc such that the following holds, such that so this has two parts. So the first part is that we take 1 over n squared expectation trace gz trace gw. So we take two traces of two traces of the resolvent at different spectral parameters, and then we take their product and we compare it with the same when I have the when I have the trace of the H prime, I have the same expression for W prime. And then we want to prove that this is order n to the minus C. And the second part reads analogously. But now we have the trace of the product of the resolvent. So GW minus trace G prime Z. So this is not the derivative, but this is the resolvent of the second Wigner matrix. I will recall it in a second. For any, now the spectral parameters are just complex, and they satisfy the following conditions. Imaginary part of Z absolute value. So now the imaginary part can also be negative in contrast to the local law. This is equal to eta, which is n to the minus 1 minus epsilon. So just a little bit better than what we had before. And we need that the real parts are close to E. And they have to be as close as 1 over n. And I'll give you time to take a picture in a second. And the G is, as before, it's the resolvent of H. And the G prime is the resolvent of H prime. So yeah, these are just definitions. And now we make these definitions for all complex numbers that are not real. Okay, so maybe you can take another picture now. And then this was the first lemma. So this allows us to compare green functions as we had in the expressions before. And now the second step will be this lemma that I already mentioned in the beginning, that will allow us to get rid of this eta smearing out of the function f. So I want to state that still before the break, and then see how we conclude, how we can conclude the proof of 2,2 then, and then we make a small break and before we go into the proofs of these lemmas. So now we remove the smearing out. So we're in the same. Well, now we'll just need one Wigner matrix, and we fix in energy E in minus 2, 2, and the positive epsilon, and then we have a function on R2. And then f eta tilde with this smeared out version that we defined in this dot. Well, I can also maybe just recall it. So now it's a bit simpler because we have just in 2 dimensions, u1, u2, and then I have an integral v1, v2, f of v1, v2, eta tilde, u1, v1, zeta, eta tilde, u2, v2. And yes, before the eta tilde, no, the eta tilde is not the eta tilde we had before. It was n to the minus epsilon times. So it was here. So the eta tilde is, well, it's eta, it's n rho e times eta. So it's rho e n to the minus epsilon. So this is, well, n rho e eta, and this is the same as rho e n to the minus epsilon. Okay, and then the statement is that we find a xc such that the difference, if I test the 2-point intensity measure with respect to f or with respect to f eta tilde, then this difference is small. So what do we have? So we have f minus f eta tilde. We evaluate it in u1 and u2, and then we integrate against rho n h e 2 du1 du2. Then this is of order n to the minus xc, and yeah, the rho n h e is the local 2-point intensity measure of a Wigner matrix H. Intensity measure at E of a Wigner matrix H. So this gives us these two steps. Let me now summarize how we then get theorem 2.2. So first of all, this formula which we derived here expresses the smeared out 2-point correlation functions in terms of resolvents. Okay, so we just need the trace of the resolvent times the trace of a resolvent at different spectral parameter, and the trace of the product of these resolvents. These resolvent expressions, we know that they are closed by lemma 2.2. Okay, lemma 2.4, which gives us these two parts, which compares the resolvent of one Wigner matrix with the resolvent of the other Wigner matrix. And but on the other hand, if I test this function here, so if I test f eta tilde against the local k-point intensity measure, then I can rewrite it as testing f against this function p. So this gives us that from lemma 2.5 and this computation which we did here, we immediately get this new goal. So maybe I should write this down. So first, let me call this equation here double dot, and then I remark this here, so that now this equation double dot plus lemma 2.4, they imply what I call this new goal. And then we can use this lemma 2.5 to remove, to replace the f again, to replace the f eta tilde again back by an f. So the new goal, when I apply the lemma 2.5 to this, then this implies theorem 2.2. What remains is the proofs of lemma 2.4 and lemma 2.5. Okay, and then yeah, maybe there's another good time for a picture, and then we can take a break till till 10:20. Or if there are any questions, I'm of course happy to answer them. Then we can continue. So yeah, now what we want to do next is then to prove, or what is left to do is to prove this lemma 2.4 and 2.5. We will start with 2.4, which we'll hopefully manage today. And yeah, then 2.5, I have to decide whether it might be homework or we can finish it next time. And yeah, as I said before, the lemma 2.4 is the main work, and we will use this telescoping idea and also this that we used last time, and that's the crucial point where that's actually the only point where this 4-moment matching will come in. And so we will actually focus mostly on this first part. The second part is then an adjustment of this, which I might or might not discuss. And yeah, so let's go into the proof, and let's start with this. So this is now the proof of lemma 2.4. And yeah, as I said, we only focus on 1. 2 is proved analogously. And now we first rewrite everything in terms of the entries of the resolvent, both resolvents. Note that the left-hand side of 1 equals to the following. So I can write it as 1 over n squared expectation sum over I and j, g j j z, g I w minus g prime j j z, g prime I w. Right? And now we want to apply the telescoping idea, and now we're in the good situation that now we have resolvents here which behave somewhat much nicer. So we now apply the telescoping sum idea, which mentioned last time in this section 2.2. And yeah, this is also as in the Lindbergh proof of the central limit theorem. So see also proof of theorem 2.3, and we apply it to the well, in some sense, to this function f, which is the argument here. So it's f being 1 over n squared sum ij g I z. Well, now I changed g and w, z and I and w, but okay, that doesn't matter. And what I really recall from last time is that we had this function phi, which was, so now we will now replace in these resolvents, we will replace 1 by 1 the entries of h by entries of h prime. And last time we, for that purpose, already introduced a function which maps pairs of indices. So I and j, I smaller than j, is a bijection to the set 1 up to gamma n, which gives you where gamma n is the number of independent entries in a Wigner matrix. So is some bijection, and the gamma n is n times n plus 1 over 2. And then we define 2 families of Hermitian random Hermitian matrices. We define the Hermitian matrices H gamma. So these we had already defined last time, but I think it's good to recall them. And we will have a new family W gamma, also n by n. And they look as follows. So Hij gamma is H prime Ij if the phi of Ij is smaller than gamma, Hij if it's bigger, and Wij gamma is just different in the entry where the Ij is equal to gamma. So Hij as before, if the phi Ij is smaller than gamma, then it's 0 if phi Ij is equal to gamma, and Hij if it's bigger than gamma. Okay, and now here I assume that I is smaller than j, and the gamma runs from 0, 1, 2, up to gamma n. And yeah, the other entries, they are of course fixed by Hermitian symmetry. Other entries are determined by Hermitian symmetry. Okay, so, okay, well, maybe now's a good time to take another picture, and then I'll cut the next picture here, so then you'll get the full information. Okay, so this was the first part of the notation, and we also introduced the corresponding resolvents. So, well, maybe first I should remark that H0 is the original matrix H, because of course all phi ij's are bigger than 0. All phi ij are bigger than 0. And on the other hand, if the H of gamma n is the H prime. So this really transports, so replaces 1-by-1 entries from H into entries to H prime, and then the W somewhat is an intermediate step which we will need to make everything work. Okay, and then we also define the green functions. Define the green functions for all of these guys. So we have an R gamma of Z, which is the resolvent of W. Then we have an S gamma, which is the resolvent of H gamma minus 1. And we have the T gamma, which is the resolvent of H gamma. And then, so yeah, maybe you can now take another picture. And what I still want to tell you is that, well, you might say that, well, S of gamma plus 1 is the same as T gamma. That's correct. But for our proof, it will be helpful to have really both of these notations, because they will come in at the same at the same place. We will have both of these things, and we want to distinguish them, and then it's easier to really have different notations for the point when gamma is 1 minus gamma, so to say, and when it's gamma here. Okay, and now after we've introduced this notation, we want to really go into the proof, and now this telescoping idea will come up again. So we start by rewriting what we want what we are looking for. So maybe just to recall, what we want to understand now is this part here. So we have we have this sum here, and then we have the expectation of the product of the traces, and we compare these two, and we want to prove that this is small. And now with this notation that I just introduced, I want to rewrite it as follows. So so yeah, we have these two traces, W minus, then the same with the primes, G, J, J, W. And now this I can rewrite with the following telescopic sum. So this needs a little check, but I'm sure after what we've done last week, and you know how to see that. So we now have an additional sum over gamma here, and then now I can rewrite this with the t's. So t of z t j j gamma w minus s I gamma z s j j gamma of w. Okay, and so we have this telescopic sum representation of what we want to understand, and because of that, and well, it's easy to see that the gamma n is order n squared. So this sum here has n squared terms. So if we want to make this part here n to the minus xi, then we have to make each of these summands here n to the minus 2 minus xi. So that's the following. Because of that, it suffices to show that I have the following, namely 1 over n expectation. So I just take part of this, I take now one summand here. Each of them should be smaller, so gamma j j w gamma minus, and then the same with the s. It's easier to write like this, 1 over n, because we'll start looking at them separately, s I j gamma z, no, s I. Now there comes the j j w, that this is order n to the minus 2 minus xi. This I want to call equation 1, and this has to hold for each gamma going from 1 up to gamma n. Okay, and now we want to split it up into two parts. So here we would have to compare this sum over the t's with the sum over the s's, but instead what we will prove is that both of them or each of them is close up to an error of this size to something which is independent of the t and the s, so to say. So let me formulate it as follows. To prove 1, it is enough to verify the following thing. So claim 1, there is an A of z and which depends on z and w, such that the following holds, such that it says now part 1. So if I take the expression above for the t, so t I e t j j gamma w, this is equal to a z of w plus an error term of the size that we had before, n to the minus 2 minus xi. And then the second one is the same, but now we have an s. S I gamma z j gamma of w is a of zw plus order to the minus 2 minus xi. Okay, and so yeah, we want the important point here is that we have one fixed a which is the same for both of them, and we have this sufficiently small error term, and then I guess it's obvious that once we've verified claim 1, we have proven 1 here, and then the lemma would follow. Yeah, maybe now is a good time again to take a picture and record these notes. And yeah, now the rest of the proof will actually be devoted to showing this A. And yeah, so we will focus on A again and B, and then explain how we would how we would get B. So we start with A, and then the idea is so you remember in this Lindeberg proof of the central limit theorem, there were two ingredients. So there was this telescopic sum argument, and then to estimate each summand of the telescoping sum, we used Taylor's theorem. And here there's an analog. We don't use Taylor's theorem, but we can use a resolvent expansion. And now that's the point why we introduce also this R, is that we will expand these resolvents here around the matrix R, which was defined with the W. So resolvent expansion of T gamma around R gamma. So now it's easier to fix gamma because, well, this is maybe I should, yeah, well, maybe I should have remarked this, but this here is of course for fixed gamma. Maybe I can insert it here. So fixed gamma, and then this A here will of course depend on gamma, but that's fine. Okay, so the gamma is fixed, and then we define a delta gamma, which is the difference between H gamma and W gamma. And that's the important quantity here, because recall that the R gamma here was defined via the matrix W gamma. Okay, and so that will be now our basic object, and then the T we will express as a perturbation of the R gamma via this delta. So we define this delta gamma, but now we omit the gamma from our notation for now. Omit gamma from our notation, and then so by the resolvent expansion, so by and I'll actually ask you to prove this in the homework that I'll post probably tomorrow. So homework 4, I think. We have the following, that T, which is actually the T gamma, looks as follows. It's a sum from 0 up to 4, R minus delta R to the L plus T minus delta R to the 5. And here everything is yeah, everywhere I omitted an R. Sorry, I omitted the gamma. Delta is delta of gamma. Okay, and now we plug in this. We plug in this expansion here into what we want to understand here. So this sum of the T's. So that then looks as follows. So it's a bit, yeah, complicated expression. So let me start with the thing that we are interested all the time. Well, now the gamma is back. Well, maybe I should remove it. So this I can now write as the expectation, and now each of these T's I will now replace by this expression here. And now I have to evaluate everything in an entry. So here I have still this sum I and j. Then I have a big parenthesis, L goes from 0 up to 4, R Z minus, yeah, maybe I should also have remarked here, so everything here now depends on the spectral parameter, and in this it's fixed. All in this expression here, everything is evaluated at Z. But now I have to distinguish here, so there's a delta. No, delta does not depend on Z. Sorry. So R of Z to the L. Then I need the II entry of this whole part. And then I have the T of Z minus delta R of Z to the 5, also the II entry. And now this whole thing in the sum is multiplied with the same thing where the when now the II is a JJ. So and I have a W minus delta R W L J J plus TW minus delta R W 5 J J. Okay, and this whole thing will be equation 2. And now from this right hand side here we want to extract the A, and there will be a part which we somewhat separated here, which comes from these two things here, which will be large. But see here, you see that it only depends on R, and then it will turn out that this will only depend on the first 4 moments of H or H prime, which are both the same. So so we will multiply out both expressions here. Then we will of course get a horrible mess. But then we will order this math into two groups. So we multiply out these parentheses here. So this times this, and split up the resulting terms, so the terms that appear from this product, into 2 groups. So they are main terms, main terms, where the power in delta, so a total power of delta, this should be at most 4, is at most 4. And these things are somewhat large, but they can all be put into W because into A, because we will see that they only depend on well, they would be the same for S and T. So are put into A, Z, W, and then there are the remainder terms, and they will be small because the W actually, the delta has a small rank, and we can use the local law to estimate this resolvence. And I'll make it more explicit in a minute. All remaining terms, they will be small, and yeah, due to local law plus small rank plus smallness of delta. Okay, so that's now the vague idea. I will make it more precise. I'm not sure whether maybe it's good to take another picture now, maybe like this. If there's something missing and you don't have a picture, then let me know. Then I can show you this part again. And so now let's make this more precise, but by really defining what I mean, what the A should be in a formal way. So we define A of Z and W as follows. So it's 1 over n squared, then I and j. And now I have an L1 and an L2. Each of them, or they should each be positive. Well, maybe it's better to write it like this, but their sum should be smaller than 4. And then I have the following. So you should think of this as these are the main. This A will be the main terms, and these come in by combining these such a term here with this term. So all possible combinations between these first two terms. So they look as follows. So I have an RZ. There's a big expectation minus W RZ L1. Then I take the II entry of such a guy, and then I have the same with the W. RW L2 JJ. Okay, so that's the A. And now we have the following important observations. So note that delta. So first of all, I want to make precise what I mean with the small rank. So if I look at an entry of delta ij, then there are only at most 2 entries. Let's make it more precise. So well, let me first write down what the result is, and then we go back to the definition, and then we can check that this is really correct. So I only have an entry in the AB or BA. Delta only has an AB or BA entry. Well, this will be equation 3. So let's go back to the definition of delta. Well, delta here was defined as the difference between H gamma and W gamma. And now if you go back to the definition of those two, then there was only a difference when the phi ij was equal to gamma, because then the W was 0 and the H, well, the H had the H ij prime entry. Okay, so there's only one entry. So these two matrices, they only differ by one entry, namely when the I and j is equal to gamma, and this is actually what the A and B are supposed to mean here. So I should have continued if A and B satisfy the following, they're chosen such that phi of AB is equal to gamma, right? That's the only entry when they differ. But that has the following consequence, namely it means that the delta is independent of W, independent of W gamma, because it just has one entry, and this entry precisely, it has this entry, and this entry was precisely set to 0 for the W gamma, and therefore it's also independent of the resolvent. So, and thus of the resolvent at whatever entry, whatever Z. Okay, but that means that if I multiply out these terms here, then I can use actually this independence, and in fact I can express everything else in terms of the R, in terms of entries of expectations of entries of R times expectations of the entries of delta. But there's only one entry here, and this will be defined because the L1 runs up from 1 up to 4, so they at most 4 of these moments appearing. So that means that the A, which I defined here, depends on H and HW, depends on H and HW only through the following two things. Well, we get the first 4 moments of W, first 4 moments of H prime, which are the same as the first 4 moments of H. Yeah, maybe I should remark it via the first 4 moments of delta, and then all of the other dependencies comes in kind of in some sense implicitly through the W. Okay, so yeah, maybe now you should take another picture, and therefore, if I follow through the whole procedure by if I follow through this whole procedure with the S instead of the R, and I redefine my delta, then I would get I would end up with the same result for A. So therefore, following the same procedure for S gamma and defining the delta by the perturbation of H gamma minus 1. Well, that was the H gamma minus 1 was the S was the resolvent of the H gamma minus 1, so that's the natural object for the difference. So this yields the same definition of the A. So in that sense, we would get the same expression. And what we want to use now is a technical result, which we will actually prove as a homework. We now use what I would call claim 2. So for any constants q bigger than 0 and delta bigger than 0, we can control the q's the q norm of the entries of R and T. So we have the following. I take an Rij entry at the spectral parameter zeta, and then I want to understand the q norm of this, and the same for the T. Q norm, this is smaller than n to the epsilon plus delta for all I and j, and zeta in being x or w, as well as well, the n has to be large enough, as well as all large enough n. Okay, and so proof this we will prove on the next homework sheet. It essentially comes from the local law and this type of resolvent expansion, and I think this is good to do individually, and then we will use this and now complete the proof of claim 1. Yeah, maybe it's again a good time for a picture. And now for this proof of claim 1, we will just have to estimate in this expansion that we had before. So in this expansion here now, we introduce we take out all of the terms that we put into A, and then we have to estimate all kinds of combinations that come in from the remaining terms. and they will have a somewhat simple structure, and they can be estimated quite quite easily by recognizing the structure. So we now use 2, which I'll go back to it in a second. So 2 was this formula that I just showed you, right? So if I look at 2 and then I subtract 8 from it, then I get the following. So this was this usual term, gamma z jj. Well, maybe I should not write the gamma anymore, but now I subtract the a. Let's get rid of the, and then the rest has the following structure. So there's an 1 over n squared, sum over I and j, and then I have some other finitely many combinations between those other terms, and these I all want to write as xij, and so I'll call 4. So c is a constant here, and the x's look as follows, where xij 1 up to c, they lie in a set M, which I define now. So so M are monomials, and they're monomials in all of these entries of T's and R's that we had before. So this is the set of monomials in entries of TZ, RZ, TW, and RW, and also delta. So each of these things here is a matrix, and then we take entries of them, and then we combine these entries to products, so to monomials. And there are a few conditions. That's where the L and the P come in, such that the total degree of the entries of delta, this is L, so this equals to L, and the total degree of entries of all of the others, this should be P. Entries of TZ, RZ, TW, RW, this is equal to P. And then, yeah, this is the whole set. So yeah, is this definition clear? So I take monomials in these entries, and then I have two conditions on the degrees. So the total degree of all entries of deltas will be L, and the total degree of entries of the T's and the R's, that will be P. And the point here to distinguish these things is that the delta will be somewhat very small, actually n to the minus, the delta entries are n to the minus 1/2, or even 0, or many of them are even 0. And then the entries of the T's and the R's, they will actually be n to the epsilon, and then we have to do some power counting to see how many of those things appear. Okay, and then from the definition, and if you look at the proofs before, then you see that P is smaller than 2L for every xij. This just comes in from the definition. This is easy to check. And that comes from this product structure, because basically you always have 2. So in here you always have 2 R's on R and a T, and only 1 delta. Okay, and then we'll estimate it as follows. So from this equation 3, which is the property here of the delta, we get the following. Namely, if I look at the L plus P norm of this entry, then this is smaller than some constant which depends on L and P, and the characteristic function that I and J is the same as AB. So remember, that was the argument where phi is equal to gamma. and then there is an n to the minus 1/2. And yeah, here I just use that the H and the H prime are Wigner matrices. So then we had this condition, these conditions on the moments, so that Hij prime or not, or maybe I write them out. So if I take a p norm of them, then this is smaller than Cp n to the minus 1/2. Okay, so yeah, maybe now you can take another picture. And then, and now with this we can, in the claim 2, we can estimate the x's. So therefore, if I take an x in LP, where the L and P are bounded, then we get the following. So I can estimate this expectation with Hölder. So that's now a product. But then this product I can write as, and take the maximum over all deltas that appear. There will be L of them, LP norm, and then I have PRs, so they look as follows: zeta Z W R I J zeta. Then I have also the L plus P norm, and then I have P of them. So, and then the same, they're also T's. Okay, and now I can use the claim 2 to estimate these here, and the, well, what I will call 5 now, to estimate the first ones here. So I use 5 in claim 2 to get the following. This is smaller than n to the delta minus L over 2 plus P times epsilon for any delta positive, and the n has to be large enough. Okay, and well, then we can combine all of those. So then we get the following. Yeah, so maybe you take another picture, and then I go to the next page, and then it's just 5 lines, and then we are done. So yeah, I want to use this, and now we use that that the P is smaller than 2L, and the L runs from 5 up to 10. And then we plug this estimate into into 4, which was the expansion with the xi's. So this was this equation here. So the maybe I should not write it too many times, but it's not so easy to avoid it. So we have the ti's, tj's, and w minus a. These we could write as the sum I and j, and we had the sum over alpha, this bounded sum, and then an expectation xij of alpha. And now we can plug in this estimate here, use that this sum here is cancelled with this. This is anyways a finite sum which is independent of n. So the whole thing here is of order n to the minus 5/2 plus n to the epsilon plus delta. And so this shows a, well, actually this shows the whole claim, because we argued that the a has to be the a of z and w. It's the same for both. So this shows claim 1 with xi being this exponent here where we have to subtract the 2. So this is xi is 1/2 minus epsilon over 10 minus delta. So this finishes the proof of claim 1. And then, yeah. And it also completes the proof of, this lemma, because the other claim will be a homework. Lemma 2.4. Claim 2, we'll do it on homework. Homework 4. Okay, so then maybe, yeah, you can take another picture, and then that's all what I wanted to say for today. If there are no other questions or comments, and then yeah, we can make a break and then continue with the exercise session a bit later then.